Really not.
Wait, there's a marker there? I don't see it.
Okay, we are in here until 11:43, so it'd be like a normal Wednesday, but all the way through 4th hour.
It is Wednesday.
Okay, so we'll start today with 11.3. This is actually what I taught in 1st hour in 2 dimensions, the dot product. What?
That makes your life easier.
It does. It does.
I'm
It'd
guessing
be funny if she
more.
accidentally taught them.
I'm gonna cry.
Okay, so if these are your 2 vectors, do you remember how we take the dot product? Mm-hmm. And so then we're just going to add U3 times V3. So we multiply the pairs of components and then add the products.
I don't like this because my U's and my V's
They look the same.
in my
Yeah.
handwriting. It's just kind of like,
Switch to a different font, Darby.
I can't.
Change to Comic Sans.
Do you not make the tail of your
Well, you
U?
see, I write in cursive like 99% of the time, so I just, my print is terrible.
So
Just use a print U.
U, V.
S. Stop.
Because like, I don't make my V's pointy. That takes too long.
Where are you going?
I'm going places.
Okay, so find me the dot product, please, of vector A, 1, 2, 3, and vector B, negative 2, 0, 4.
Yeah, I need to get home. I left my house at 5:45 yesterday. I left my house at 5:15 to go to school at 5:45. Left my bus and then got home at 11. And I drove home and I got back.
How'd you know at 11:20 the game didn't go in like forward?
Because the bus broke down. We had to drive to varsity at like 4 miles an hour.
Okay, this is
It was fun.
What's the dot product, Gabe?
It'll be -2, 0, 12, something like that. I don't know.
it's not a vector.
So 10?
See, I was adding those things. Yeah.
Mm-hmm. So 10. Negative 2 plus 0 plus 12 would be 10. Are we good with that? Okay. Let's just recall some of our properties about dot products. The dot product is commutative. Since it's a multiplication operation, we can distribute the dot product to a sum. What do you get when you take the dot product of U and the 0 vector? A scalar of 0. Okay. I guess I also should go back and point out the dot product is our way of multiplying vectors and getting a scalar. Here in our next lesson, I'll teach you a way of multiplying vectors to get a vector. That's called a cross product. Our dot product, where we literally use the dot, okay, is a way to multiply vectors to get a scalar. Okay, so let's say we have a dot product, and that dot product is being multiplied by a scalar. Okay, you don't distribute through a product. If you have 2 times 3 multiplied by 4, you don't distribute 4 to both of them. You multiply 2 and 3, and then you multiply 4. Okay, so if we have a dot product multiplied to a scalar, that scalar can be multiplied to one of the vectors before the dot product, or you can take the dot product and then multiply by the scalar. Whichever way you want. Okay? And then what I think is kind of cool is that the dot product of a vector with itself, anybody remember what it is?
Itself.
Squares.
Yeah. Okay. So, what can we do with the dot product? The angle between u and v, the cosine of theta equals, do you remember? It's a fraction.
It's something
Is
over
it
the dot product.
over the magnitude.
No, this is
The dot product over the product of the magnitudes. Good job, Pod 4. Put them together nicely.
But how about when it's a three-dimensional thing?
Huh?
How does it work when it's three-dimensional? There can't just be one angle between them. Can there?
So if there's two vectors, you can create a plane. And that plane,
That's where
whatever
they
plane,
coexist.
that's the angle that we're going to find.
Okay.
Okay?
Visualize that because I really don't understand what you said.
We're gonna
Okay,
expand
so how many points does it take to create a plane?
Infinity?
3. So if we have two vectors in standard position, so they share the 0, 0 coordinate, and then this vector goes to this point, this vector goes to this point, we can create a plane through the two vectors. And in that plane, we can measure the angle between the two vectors. Yes?
Yes.
Okay. So let's find the angle between vector 3, negative 1, 2, and vector negative 4, 0, 2. Our dot product is what's our dot product? Negative 8, thank you. We have negative 12 plus 0 plus 4 gives us negative 8. The magnitude of u, we have 9 plus 1 plus 4. So radical 14. The magnitude of v, we have 16 plus 0 plus 4. Okay. Now, please be careful when you plug into your calculator. We need to punch in the inverse cosine in degree mode. But we have a product in our denominator, which means when you plug this into your calculator, that product better have parentheses around it.
We really couldn't craft it that much for just
Huh?
How would it get mixed up if I had it written like that?
So if you plug in negative 8 divided by square root of 14 times square root of 20, PEMDAS says we're going to divide left to right, so we'll do this division.
If I don't do like a multiplication symbol between
It's going to assume multiplication.
that's
Unless you just do that thing where you literally have one
That's what I
after the
always
other.
do. Yeah. Okay. That's
Then that's okay.
I ain't
Not everybody has those capabilities. So. What's our angle? I don't think I even ever wrote it down. What? 118.
Degrees.
1 by 6.
Yeah.
Yeah.
Now it looks like a 9. That's okay.
It's an imaginary.
Okay. What else can the dot product help us with? What were to happen? Well, okay, let me back up. What does it mean to be orthogonal?
There's a 0 in there.
Perpendicular. There's a 0 where?
If the dot product.
Is that what you're gonna say?
Something was wrong.
Yeah. Okay, so we know that the cosine of 90 degrees is 0. So if this whole entire fraction is 0, we know that the inverse cosine of 0 is 90 degrees. So how does a fraction become 0 if its numerator is 0? So if our dot product is 0, then we say that our vectors are orthogonal. Or in other words, they're perpendicular. Okay. When we were in 2 space, don't write this down, but when we were in 2 space, we could write the magnitude of our vector times the cosine of the angle to break down the horizontal component, and we could write the magnitude, times the sine of our angle for the vertical component. Now,
Wait a
somebody,
second.
what? Okay, somebody asked me yesterday, how do you find the angle between two vector, or how do you find the angle of a vector in 3 space? Okay, well, we don't find one angle, we find 3 angles. The angle from the positive x-axis, the angle from the positive y-axis, and the angle from the positive z-axis. So,
And
these are what are called our direction cosines. What did you say? Joe?
Oh, no.
Okay. Okay, so here is a vector. It could be going anywhere.
The midnight train.
So do you just take the angle from assuming its starting point is the origin?
Well, we're always going to think of vectors in standard position, and standard position would mean, yes, that they begin at the origin. So first we're going to find alpha, and alpha is going to be the angle between our vector I and whatever our vector v is. So let's just say that this is vector v. Okay? So if we were to find this angle here, we would set up that the cosine of alpha is the dot product of v and I over the magnitude of v times the magnitude of I. Well, what's the dot product of v and I?
V.
It's the first thing would be.
It would just be the first component. We'll describe it as v1.
Wouldn't it just be faster to write over magnitude of V since the magnitude of I is 1?
Okay, yes. So here is how we find alpha.
Oh, so you just do that for all three.
Pretty much. Okay. Here is vector J, and beta is the angle between vector V and vector J. Okay. So, to find that angle, we would take the dot product of V and J over the magnitude of V times the magnitude of J. But the same kind of thing is going to happen, right? The dot product between vector V and vector J is just going to be the second component, and the magnitude of J is 1, so we don't really need to write it. Let's use it. Okay. And then
Gamma time.
Is that supposed to be a fun on hammer time?
Yeah, kind of. Gamma time.
here's vector K, angle gamma is going to be the angle between those two. So the cosine of gamma is going to be the third component over the magnitude of B. Okay, so two things here. We can write vector V like this. So magnitude times the cosine of alpha I, magnitude times the cosine of beta J, magnitude times the cosine of gamma K. And I have one more cool trick about this before we do an example.
But aren't I, J, and K all equivalent to 1?
Well, this is 1 0 0
Oh,
0 1
okay.
0 0 0 1. Alpha plus cosine squared beta. This is something special. Any thoughts about it? Well, what is cosine of alpha, just in general? It's V1 over magnitude, right? So let's square those. Plus cosine beta would be this.
It's a unit vector.
Well, v1 squared, does that act as a dot product? Because of the magnitude. Oh wait, that's just a
Well, keep going with where you were going.
number. Oh. Because the magnitude of v squared is v1 times v1 plus v2 times v2 plus v3 times v3. And that's what the top is. So then we add them all up.
V1 squared plus V2 squared plus V3 squared is the magnitude squared. right? That's what's underneath the radical in our magnitude. So without the radical, it's the magnitude squared. So,
it's 1/3.
no, just one.
Oh, yep.
Okay. So let's practice with vector v equaling 2I plus 3j plus 4. Okay. Oh, for crying out loud. All right, so we know that the cosine of alpha is the first component over the magnitude. Somebody yell out the magnitude for me. Radical.
29.
Thank you. So in your calculators, please take the inverse cosine of 2 over radical 29. And share this.
68.199.
Excellent. Cosine of beta is the second component over the magnitude. So if we take the inverse cosine of 3 over radical 29, we get 56.145. Okay. And then the cosine of gamma is the third component over the magnitude. So if we take the inverse cosine of 4 over radical 29, we get
42.031 degrees.
okay. So vector V is 68.199 degrees away from the positive x-axis. It is 56.145 degrees away from the positive y-axis. And it is 42.031 degrees away from the positive z-axis. We do have a first octant vector, so it would make sense that all of these are acute, right? Okay, one more item of business, and we'll take our little brain break. Remember
I
that?
told it would happen. Oh.
The projection of V onto W is the dot product over the magnitude of which we are projecting onto squared.
This is 100% one of those things. Where it's just like, I need to memorize this for this test.
Times W. Okay.
Mm-hmm.
I always forget which one's on which one.
Yeah. I was thinking it's W under V because it's W/D.
So the subscript of what is where you're going is what you're going on to.
Well, I think shadows do it.
Okay, so we have vector W and we have vector V, and the projection of V on to W looks like this. Ooh, I drew it a little bit too far. I'm very sorry. Maybe I'll extend. Now I'm making it worse. There. I feel a little bit better about that one. Okay? It's like our shadow. Okay? So I had two vectors over here. from earlier in our notes, we had vectors A and B, 1, 2, 3, and negative 4, 0, negative 2, 0, 4, excuse me. Which projection would you like to find?
A onto B.
The projection of A onto B. So we already found the dot product, yes? Even if we forgot it, it's easy to find again. What was it?
10.
10. Over the magnitude of your subscript vector squared. So the magnitude of B,
It's 20. Radical 20.
okay, so squared would be 20. Good choice. Good choice. And then we're going to multiply that to which vector?
B.
So the projection of A onto B is going to be the vector negative 1, 0, 2. I didn't even know that was going to happen.
That's nice.
Isn't it?
That's nice.
This is epic.
Yeah, isn't that
Okay. So we're going to take a little brain break.